Somewhere in the history of human thought, a question was asked so large that most people instinctively look away from it. The universe, all of it, everything that exists, has a shape. And that shape is knowable. That claim alone should stop the mind cold. Because the universe doesn't just contain objects with geometry. The universe itself has geometry. Space is curved, or flat, or wrapped in on itself in ways that make ordinary intuition buckle. And physics, specifically general relativity, gives a framework to ask which one. Albert Einstein's field equations describe gravity not as a force, but as the curvature of space-time. Mass and energy bend the fabric of space, and that bending governs how everything moves. But Einstein's equations do something else, something more radical. They describe the shape of the entire universe as a single geometric object. Pair those equations with the cosmological principle, the well-supported idea that the universe looks roughly the same in every direction and from every location at large scales, and the possibilities for universal geometry narrow to three fundamental classes: positive curvature, negative curvature, and flat. Consider the positively curved universe first. Picture the surface of a sphere. On that surface, parallel lines eventually meet. The interior angles of a triangle add up to more than 180 degrees. Now extend that idea into three full dimensions. A hypersphere, sometimes called a three-sphere. A universe with positive curvature is finite, but has no boundary, the same way the surface of a ball is finite, but a person walking along it would never hit a wall. In such a universe, travel far enough in a straight line, and the path curves back to its origin. Light emitted in one direction could, theoretically, circumnavigate the cosmos and arrive from the opposite direction. This is the spherical universe, and general relativity allows it when the total energy density of the universe exceeds a critical threshold. For decades, physicists watched this possibility carefully. The discovery of cosmic acceleration in 1998, the universe expanding faster and faster under what's called dark energy, made the spherical model harder to sustain, though a 2020 reanalysis of Planck satellite data briefly reignited the debate by suggesting a slight positive curvature signal in the cosmic microwave background. The negatively curved universe bends the other way. Imagine a saddle, or the flared mouth of a trumpet. On this geometry, parallel lines diverge, and triangles have interior angles that sum to less than 180 degrees. Extended into three dimensions, this is a hyperbolic universe, infinite, open, and expanding forever. General relativity permits this when the energy density of the universe falls below that critical threshold. The hyperbolic universe is deeply strange to visualize because the space itself accelerates away from any central point, meaning distant regions recede faster than the speed of light, an allowed consequence of space expanding rather than objects moving through it. Some evidence from the cosmic microwave background has at moments hinted at a slightly open geometry, but the signal has never been strong enough to close the case. And then there is the flat universe. Here, the geometry of Euclid holds perfectly. Parallel lines stay parallel forever. Triangles sum to exactly 180 degrees. The flat universe sits at precisely the critical energy density, the knife edge between collapse and eternal expansion. This is the geometry that current measurements most strongly support. Data from the Wilkinson Microwave Anisotropy Probe and the Planck satellite, instruments that map the cosmic microwave background with extraordinary precision, found the universe to be flat to within about 1%. That is a staggeringly tight result. The flat universe appears to be infinite, extending without boundary or edge in all directions. But here is where the story takes a genuinely strange turn. Flatness describes local geometry, the curvature of space at any given region. It says nothing, on its own, about the universe's topology, which is its global shape, the way its regions connect to one another. A flat universe could still be finite. Imagine a video game screen where a character walking off the right edge reappears on the left. That surface can be flat, no curvature, while still being finite and closed, wrapping back on itself. Mathematicians call these constructions flat tori, or more exotic variants, and they are perfectly consistent with general relativity. In such a universe, light from distant galaxies could wrap around and produce ghost images, the same galaxy visible in multiple directions at once. Cosmologists have searched the microwave background for these telltale repeating patterns and found nothing definitive. But the search continues, and a finite flat universe remains a live possibility. There is also the question of what lies beyond the observable universe, the sphere of space from which light has had time to reach any observer in 13.8 billion years. Even if the full universe is infinite and flat, only a finite bubble of it can ever be seen or measured. The true extent of what exists may be permanently beyond reach, which means the shape question carries an irreducible humility at its edge. Based on the best available evidence, the flat infinite universe is currently the leading model among physicists. The measurements agree with it. The mathematics of inflation, the theorized period of exponential expansion in the universe's earliest moments, naturally drives the geometry toward flatness, explaining why it sits so close to that critical value. The flat universe is the picture that fits the data without requiring additional assumptions, and yet the universe keeps the final answer just out of reach. A flat universe could still be finite. It could still be topologically exotic. The curvature might be so slightly positive or negative that current instruments cannot distinguish it from perfect flatness. The universe is shaped. Of that, physics is certain. The shape appears flat. Of that, the evidence is strong. But whether that flatness extends to infinity or curves back on itself somewhere beyond the horizon of the observable remains one of the most genuinely open questions in all of science. The cosmos, it turns out, offers its geometry willingly and its full topology only reluctantly.